Good afternoon, everyone, and a very warm welcome to today's R-ladies Bangalore workshop. I'm thrilled to see so many of you today on a Saturday afternoon. So, first, let me introduce myself and the other co-host. I'm Shruti. We are based out of Bangalore. We are the R-ladies Bangalore chapter, and the other co-hosts are Anjali and May, and we are always there to answer any of your queries. So do not hesitate to ask. Right? So for those of you who are new to Our Ladies Global, so Our Ladies is an initiative which are dedicated to promoting gender diversity in our community. It's a women-led organization with chapters over 200 cities across the world. This is all volunteer lead organization. So where we conduct free meetups, mentorship programs, and workshops, all with the aim of empowering every voice in data. So before we start, there are some housekeeping rules. First of all, please keep yourself muted during the session. Only communicate via chat whenever it's necessary. And there will be a question and answer sessions after the talk. So please keep your questions and queries ready for the speaker after her presentation. And do not hesitate to ask questions if you have any doubts. Remember, all questions are important. We are going to upload the recording of this session on our YouTube channel in few days. So I will share the link now. Just give me a second. This is our YouTube channel. Do join the channel for our previous sessions as well. Okay. And at the end of this session, we are going to provide a feedback form. So do please fill it up. Fill it up so that it will encourage us and help us to do such more free workshops in future. So before any further ado, let me introduce you to our speaker, Dr. Rema. She comes with a 12 plus years of experience in the higher education sector. She is presently serving as an assistant professor at the Department of Data Science and Analytics, School of Social Sciences at MS Ramaiah University in Bangalore. She is also heading the university's Center for AI for Social Good. She has completed her PhD in applied mathematics and her research works on stochastic modeling and queuing in healthcare sector. She is also a two-time gold medalist in both her PG and UG and holds a Lean Six Sigma Green Belt certification. So, ma'am, we are very thrilled to have you here and thank you so much for doing this. Over to you, ma'am.
Thank you. Thank you so much, Shruti. That was indeed a very nice introduction. Thank you so much. I'm delighted to be part of this session today. I want to thank Our Ladies Bangalore chapter for having me for this interactive session. Particularly, I want to thank Ms. Mayberry who invited me for this session. Thank you, May. Really appreciate that. So I understand that we have a heterogeneous audience today. And I would probably, want to spend 5 minutes, maybe with a quick introduction. You can probably tell me if you're a student or a faculty, maybe on chat, or you can also unmute, and then we'll get started. Since we are online, I think, if I keep talking, you might not really be interested. So I would like to try and have it as interactive as possible with discussions as we go by as well. I hope that's all right.
Yeah,
Okay, Vani, Vani, researcher, great. Okay, I'd like to get more in chat. Okay, Nita, PhD student, Pooja, faculty, great. Sandeep, postdoc, all right. Debjyoti, PhD student, project assistant, Devanji, okay. PhD student, Reverend, all right. Vinita, PhD student, okay, great. All right. Shrikanta, MSc student. Okay, wonderful. Dr. Soham, delighted. Kirtana, PG student at SRM. Okay. All right. Great. Thank you so much. So I really have a diverse audience here. So I'll try and cater, to this to the best extent possible. Anjali, yeah, MTech student at NUS, data consultant. Great. Wonderful. Yeah, thank you so much. So, I've been asked to look at this session from more a beginner as well as to an intermediate perspective. And today I'm going to be speaking about time series analysis, particularly focusing on model building. I'll be looking at exponential smoothing model, ARIMA model, as well as the neural network autoregressive model. So as I take you through the modeling part, I will be doing the modeling part. I'll be sharing my screen, doing it using R programming. Okay, so I will also be sharing the data set. So it's going to be just interactive through a data set that I will be, working on. And as we go by, we'll understand the various nuances and concepts related to time series. Okay, so that's exactly how I'm going to go ahead. So I hope that sounds okay. Maybe a thumbs up or a quick reaction. All right. Okay, perfect. Okay, thank you. Okay. So let me begin. Just give me a moment. I'll share my screen. Shruti, you must probably enable screen sharing because it says the host is disabled participant screen sharing.
Okay, all right. Let me just do
Yeah,
that.
sure. Yes.
Give me 1 second.
Sure.
So I've given you the host access, so you should be able to share
Okay.
the.
Yeah, sure.
Yeah.
I'll do that. I'll do that. So I hope you can see my screen.
Yes,
Okay.
you're visible.
Oh, okay. All right. Thank you. Okay. Right. Okay. So the agenda for today's discussion is going to be outlined in this manner. We'll speak a little bit about time series, where it is used, understand its components, then move to understanding how to model time series data in R. That's the agenda for today's session. I will take you through the modeling steps on how you prepare your data, how you build the model, look at model fitting, forecasting, and also model validation across three models. We'll start with exponential smoothing. I will take you through the ARIMA as well as the NNAR, and we could wrap it up with the Q&A, or in the interim, if you have questions, you can feel free to discuss. So since I will be taking you through the R, I will be sharing the data set. So in case you're working with your laptop, you have your laptop in front of you, you're working on R, you can do it along with me. I will also be sharing the code file. Otherwise, you can watch through the demonstration to get an understanding on the entire process as such. Okay. So that's exactly how I'm going to go about this entire discussion. Okay, so just give you a picture or a pictorial representation of time series data. So can I get some inputs on what do you think is time series, where it is used? How do we understand time series? Maybe quick responses on the chat would be good. What do you know about time series? Yeah, historical trends, Sanjay says. Yeah, okay. For any data points that vary over time, longitudinal sample data points, weather forecast. Okay, great. All right. Change of continuous values over time. Okay, so perfect. So let's, yes, change analysis. Perfect. Okay. So if you have to mathematically look at time series, your independent variable is going to be the time, and you are studying the changes of any particular variable over a period of time. So I have given you two plots, one where on the left-hand side you see share prices which are varying over a period of time. And on the right, you see another plot where we're actually looking at changes in gold prices. Now, why time series analysis? So time series is a very popular predictive modeling technique. It comes under the class of predictive analytics, where forecasting is something that you're really looking at. So can I predict if I have historical trends? That's, as one of you pointed out. If I look at the past uh, values of the variables, I could be studying maybe the share price, I could be studying exchange rates, I could be looking at gold prices, I could be looking at demand for a product, right? So in any of these contexts, looking at the past values, can I predict how the future is going to be? In the sense, can I get an understanding of how the future values of the variable would be? Okay, so this is where time series is used. Time series has a large or a broad horizon of applications, particularly in finance. I told you a couple of macroeconomic variables that you might be interested in predicting and forecasting from a business perspective. I have closely worked in the healthcare sector. I did my PhD in the healthcare analytics, where I extensively use time series to model short-term forecasts in the sense I have data in the hospital, say in the emergency department, right? So I have uh, the data of walk-in patients, basically operational data, and timestamps of when they've, come in. Can I look at a scenario where I can predict in the next, say, 1 week, how will my demand be? How will the patient turnover be? Okay, so this is one of the examples that you can connect with. So wherever prediction is looked at, predictive analytics, as we speak about, in addition to the various regression techniques which form the large class of predictive models, time series are very, very critical here. Okay, so having said that, we're looking at the importance of time series. Let us deep dive a little into the components of time series. Okay, so I'm moving further. Okay, so I'm just going to take you through these four figures. I just want you to take a look at that. Any quick comments? What can you see in each one of those figures? You can point out to any one of the figures and tell me what do you see there? Do you see trend? Do you see some random variations? Any quick responses on the chat? Yeah, trends in figure 1, 2, there is a pattern. Okay, so right, very good. Okay, great. Thank you. First one is growing drastically over time. Yes, spikes in regular interval. Great. Okay. So largely when we talk about time series and its components, okay, there are four components that you can divide your entire time series data into. Okay. Uh, the first figure that I want you to understand talks about trend. So whenever we talk about trend in time series data, it represents either a steady increase or a decrease. Okay. Now, in what kind of data can you see this? Probably in population data. Let's say you're studying population of a country over several years. You will see a steady increase, right? Let's look at, say, population of India. If you look at, say, modeling epidemic outbreak, for example, you're looking at number of COVID cases, right? Or say number of dengue cases. I look at any study in epidemiology, I'm going to see a trend, okay? Sudden spike or a sudden increase over a period of time. I look at, say, sales data of a particular product, I can still see trend. So largely, a lot of time series data show you the trend component. But is trend the only component? Not really. You have other components of time series which need to be assessed. That's where I'm moving to figure 2, where in figure 2, I want you to see that we have a combination of trend as well as seasonality. Okay, so why trend? Because I see it a steady growth, there is continuous increase. While if I look at the variations year, year on year, right? Year on year, I see similar patterns as well. So whenever I have pattern of changes repeated within a year or year on year, this is indicative of seasonality. So you might see something like a sinusoidal pattern, repeated spikes, right, at a particular frequency or periodicity, as it is called. Now, in what kind of data I can imagine seasonality? Let's say we look at demand for, say, air conditioners, right? You see it summer after summer, or say demand for gold or flowers, etc., during festivals, right? So it has a periodicity of repetition, usually year on year or within a year. Okay. So if I look at figure two, it's a combination of trend as well as seasonality. Now, when I look at figure three, okay, what do you think figure three shows? Is there a trend? You think there's a trend there? Do I have seasonality? What does the visual tell you? Yeah, there is seasonality, yes. So when I look at figure three, I don't see trend. Okay, so when I say trend, I have to see the graph steadily moving up or coming down. So it's, yeah, perfect. So it's like a constant trend. But I have seasonality, which means within years, I probably have repetitions. But I have another pattern, which is called cyclicality. Okay. So when I talk about cyclicality, we look at some kind of a repeat pattern after a particular period of time, which is usually where the periodicity is more than 1 year. Okay. So classically, if I look at, say, business cycles, I might probably have the periodicity of the highest growth in business, say, once in 3 years or something. Okay. So if I break that down, you can break this entire graph down in figure three into, say, like three parts, where I probably see a same repeated pattern after, say, about 5 years. Okay. That is cyclicality. So when I'm looking at a repeat pattern with a larger periodicity, or a similar pattern after, or which is usually more than a year's time, say once in 3 years or once in 4 years, I see that kind of a pattern, that is cyclicality. So my figure three could be a combination of, say, seasonality and cyclicality. Okay. When I look at figure four, what do you look at figure four? What sense? Is there any pattern, or it's just noise and it's random? I don't see any pattern, right? So figure four is basically the random component. And when I look at random component, this is basically the component which cannot be typically modeled. Okay. Now I can have erratic variations in time series data, maybe because, yes, it's noise. There could be, right, Monalisha. So there could be sudden, say, some political instability where I see some drastic variations or some decisions which are taken, which can change the share prices very, very erratically. All right. So when I'm trying to understand time series from a mathematical modeling lens or a modeling perspective, largely, if you have to model time series, you have to understand what are the components here. A given time series data could probably be a combination of trend and seasonality, or trend cyclicality, or maybe just trend, and finally coupled with random variations. So when we talk about modeling time series, it is basically assessment of the components of time series on whether you have trend, or you have trend and seasonality, you have seasonality, cyclicality. Analyzing this part is the essence of what you do in modeling. Okay. So it is important to understand the components of time series as a very, very preliminary understanding before we head to the modeling. So I hope we're good so far. Are there any questions? Are we good so far? Okay, great. All right. So what I would do is I would just give me a minute. I would share the data set and the code. So I'm going to move to the first discussion on exponential smoothing models. Okay. So before I do that, just give me a moment to. Um, yeah. Okay. I just want to check, is the file share disabled? Because I'm not able to see a file access here on the chat. Shruti or the host, if you can just
You
help
are the
me.
host now, so I guess
Okay.
you can share it.
I can only see a drive folder, but I'm not able to see the.
Yes, I think you can only share the link.
Okay, okay, okay. All
Yeah,
right. So probably,
like
yeah.
drive link and where they can download it from.
Okay.
Can't
So
share
just give
file
me a
directly.
minute.
Yeah.
Got it. Got it. Just give me a minute.
I hope everyone is on their laptop or computer so that you have access to R and practice the
Yeah.
hands-on.
Just give me 5 minutes. I will just set this up
Yes, yes,
and
ma'am. Yes, ma'am. Please
yeah,
take your time.
sure. I'm just sharing the link. So I've just shared the data set. So you can download that.
Yes, I can see the link.
Yeah. So those who are working with me could do it parallelly. Alternatively, if you think you just want to watch it, I will also be doing the demonstration. What I'll also do is just share the text file, the code file. Okay, yeah. So there are two things I've shared. I have shared the code file. That's just a text document. And I've also shared the data set, which you can download. I'm straight heading to the R screen. So in case you're parallelly working with me, yes, please go ahead. Alternatively, you can just watch the demonstration. So I'm just going to go to the R screen. Yeah. Okay. Just give me a minute. Yes. All right. Okay. So I'm assuming you can see the R screen. Okay. Yeah.
Yes, can see.
Okay. All right. So, first of all, we are all in the era of AI. So, I want, I'm sure all of you are using maybe Gemini or ChatGPT, Perplexity, or DeepSeek to do your coding, right? So, today I want to kind of emphasize that it's important to give the right prompt to code. You need not really learn every piece of code, right? Because you can do the coding using AI, but a conceptual understanding on what to use when, which model has to be applied in what context, what are the assumptions of the model, how do you do the model validation? I think I'll be more interested in sharing those snippets. So very quickly we'll get the results, and also I'll also run you through the code structure so that you're familiarized with how it is built, right? So while AI will give you the code, one must also know how the code structure is, what are the arguments, so that it'll always help you debug at a later point in time if you encounter issues. Okay, so that's given that background. I'm going to go ahead and import. So I think everyone is familiar with the R interface. Probably some of you also code on Python. I use both R as well as Python, and I'm comfortable with both. So I will be showing you using the R here. The first screen that you see is where you have it as a script file. That's where you'll put your code. Where you see I'm highlighting things. That is your script file or the place where you'll code. This is our studio interface. Where you see environment is empty, that's why you're going to upload your files, right? When you're describing your variables, etc., it will be visible there. My outputs are going to come up on my screen, the third quadrant, which you see there. I can clear it with Control L. And all my plots, packages, help functions are visible on the last quadrant. Okay, so this is the interface of the RStudio. I'm going ahead importing data set. It's a very simple Excel data set. That's a data set which I've shared with you, which is nothing but daily sales volume of a particular product. So I'm going to import the data set. So I have dates as well as the sales volume. And I'm just going to go ahead and import. All right. Okay. Just, yes. So this is a data set with 243 observations, which is nothing but daily sales volume. And we'll look at prediction of sales volume here. Okay. So you can view the data set. Please feel free to, ask any questions in the interim as we're running through the code. If you have any particular clarifications, you can also put it on the chat. Okay. So we always set the data as a data frame, okay, which is a more structured format. So I convert it as a data frame. So at the end of every code line or anywhere there, this is for beginners who might be using R, either you do a control enter or a run button. Your code will be executed. And as and when it's executed, you're going to see the output in the screen here. Okay. Wherever you have a hashtag, anything followed by a hashtag is a comment line. Okay, so that's a non-executable code. It's basically used to improve the readability of your program. So let's take a look at the structure of the data. So this is a data frame. I just have the date, which is read as a character, and I have the sales volume, which is in numbers. Okay. Now in R, there are two packages which are important to be installed to carry out time series analysis. That's the T series package and the forecast package. So to know more about packages, I'm just clicking on the package in the fourth quadrant here. So when I click on the package here, you can read more about packages to get more information, right? So when you're doing it for the first time, you will always install it. But once it's installed, you only need to load it. And the loading is done by the library. Since I already have it installed, I'm just running the library here. Now, when we are looking at a typical ML approach, we always divide the data into train and test. Okay. So when I say train data is basically used to build your model. So the model is going to see that part of the data and you get your parameters. And the part of the data that you call as test is where you are going to be looking at your model validation. So that's like the unseen data that you bring up to see how well your model works. All right. So when you're working on your data, so the usual thumb rule is like 70-30 ratio, which means I look at training or building my model with 70% and I have the 30% to test. Now, when you're working with different models, let's say you're applying a regression or something, you tend to generally do a random split, which means you set seed and you do a random split, which means your entire data, let's say you have 1,000 data points, you divide them randomly into 70 and say 30 ratio or 80-20. Okay. But you can't do that in time series. That is something that we need to understand because in time series, as we know the characteristic of a time series data, there is historical dependence. So I can't randomly divide and take any 70 data points and 70% and 30% or 80-20. It has to be in an order because ordering is a very inherent property of time series. So this is one thing that we need to keep in mind whenever we're dividing it into train and test. So I'm going to divide, which is why I have done a very careful split here, not a random split. I'm dividing the data from the first to 170 observation, that's like 70% of it. I divide it into train, right? And when I do the train, so you can see that I have the first 170 observations taken as a train. What I'm doing is I'm just calling for the second column. I'm defining y as my variable and calling for the second column because the second column is my sales volume data. Okay, so head will basically give you a preview of my first few data points. So let's plot this. Main is, I'm just going to take you through the plotting arguments. I'm plotting Y here, which is my sales volume. That's 70% of my sales volume data here, okay, which is the 170 observations. Main will give you the title. You can give X lab and Y lab, which is basically going to be the labels. The type is going to define how the graph will look. You'll have those little circles there. LWD stands for line width, and you can give a color of your choice there just to make it more aesthetic. Okay, so this is the time series plot which we get. Okay, all right. So looking at this time series, any quick observations? We looked at components of time series. So visually, do you think it has trend? It has seasonality? What do you think it has? I just have the first 170 observations which I'm plotting. Can I get quick responses? Yeah, it has
Sigmoid
both probably.
sometimes.
Yeah, okay.
Sigmoid
So
sometimes.
yeah. So please understand that this is a very small part of the data that you're seeing to be able to get insight. If I probably plot my entire data, I can still get some perspective visually, right? But we need to go beyond to model to find out what exactly can be a good fit here. Okay. Right. So in R, right, whenever you're working with R, it is important to get your software to understand that you're working with a time series object. So what you do is you convert your data, which is labeled as Y, and you apply a TS function on it. TS function basically is going to convert it to a time series object. Now, there are two reasons why we are doing this. One, for the software to understand that this is time series, so it'll index it by time. And converting to time series object is important to use forecast functions also, which are sitting in those packages of T series and forecast. Okay. Now, before I take you through the exponential smoothing, I'm going to spend just about 5 minutes giving you a brief overview about that, a little bit of the theoretical context, and then I will come back to exponential smoothing here. We'll directly apply the model here. Okay. So I hope you're good so far. I will always pause and breathe so that we are on the same page, right? So can I move on? I hope to get some reactions. or a response on the chat. Okay, perfect. All right, great. So exponential smoothing models are very popular models used in time series, and typically you start applying time series modeling using exponential smoothing. Okay, so it was proposed way back in the 1950s. And the logic behind this model is based on weighted averages of the past observations, right? So I'm going to look at uh, giving weights to the previous or the historical data points to figure out my future forecasts, right? That's the basic concept behind how your exponential smoothing model works. So in that light, when you're giving weights, you have some parameters. You have something called as a smoothing parameter, which we will look at as we go further. So we have something called as a state space models. Exponential smoothing algorithms can be broadly represented as a three-string framework. So when I represent a model with an X, Y, and Z, X talks about the type of error that you have, whether it's additive or multiplicative. I'll talk about it a little more in detail. Y is going to tell you what kind of trend is there, okay? Whether trend is there or not. And yeah, I'll answer you, Neeta. And Z or Z basically stands for the multiplicative, I'm sorry, it's going to stand for the seasonality. Yeah, so when I say weights, I'm talking about the importance here, right? When I say weights, I'm not manually giving any weights, but it is the importance of past data observations which will have an impact on the future. And that is basically going to be defined by your smoothing parameter or alpha. So you'll see that when you're modeling using exponential, if my alpha value is going to be very close to zero, it means that very lower weight is given to the most recent observations, and the model relies more on the previous periods. But if I see that alpha, that's my smoothing parameter, is going to go towards 1, it would mean that the recent observation has a greater impact on the future. So diagram or graph, Mona Lisa, so we'll be looking at the forecasts. Okay, so we'll be getting the linear or the forecast values. I'm just telling you the basis of the exponential smoothing model. So I will be running it on R, and I will, we will be generating the forecast. So you will understand how the model is fit, what are the parameters there. Okay, so you could probably ask me if you have questions when I show you those plots after fitting and after we generate forecasts. Okay, so I hope that works, right? Okay, so I'm basically doing this to help you understand whatever outputs we are going to get and see when we apply exponential smoothing. Okay, that's the reason I'm doing this. And how do you get your model parameter in exponential smoothing? It is by minimizing your mean square error. Okay, so let us fundamentally understand when we talk about modeling, what are we doing in modeling? Whenever we talk about modeling, we are trying to estimate the parameters or the coefficients. I will take an example of regression model. So if I say y is equal to mx plus c, simple linear equation, okay? Y equal to mx plus c. I'm not writing here because I want you to hear and, internalize. So when I say y equal to mx plus c, y is my dependent variable, x is my independent variable. What's my parameter here? My parameter is a slope, which is m, right? I also want to find my intercept, which is c. So only if I get, so if I'm looking at say y is equal to mx plus c, just to simplify, if I have to predict y, I need both m and c. So I call m as my model parameter, which is nothing but the coefficient. So it will tell me for every unit change in x, what is going to be the change in y. Okay. So whenever we say modeling, it means you're trying to find parameters. That's exactly what we're going to do. Okay. So I want to give you a taxonomy of different exponential smoothing models, which you see there on the screen. So through exponential smoothing, you're basically determining what kind of trend, what kind of seasonality is there, and what is the nature of your error. Now, usually whenever your variance is constant across time, okay, you tend to use additive error models. And for increasing variances, we will use multiplicative error models. Okay. Now, when I say additive model, I'm probably looking at something like trend plus seasonality plus a random component defining my time series. But if I look at a multiplicative model, it's like a product of the trend, seasonality, and the error component. Now, one does not do it manually. When I run this ETS algorithm, okay, on my software, I will get the best fit exponential smoothing model for a particular data. Okay. And these are the various 15 different classes of models that I can have. So either there is no significant trend and seasonality, which means it's just a very basic, model which can be predicted with its mean value. Like I might not have any significant trend, I might not have any significant seasonality also. That indicates N. You should know this context and the notation. So N stands for no significant trend, no significant seasonality. But when I look at A stands for additive trend and additive error. So if I look at, say, AN, if I'm modeling an exponential AN, it means I have additive trend component. I'm going to look at whether there is, each of the notations. When I look at AD here, it could be an additive damped trend. What do I mean by a damped trend? This is another concept you should know. Whenever I say damped trend, it means over a period of time, my influence of trend will weaken, which means after a particular point in time, it's going to just flatten out. Okay. So, unlike maybe an epidemiology data where there is an outbreak or a population data, I see continuous increase. Okay. That trend is different from a damped trend. When I say damped trend, after a point in time, it's going to decline or just flatten out. Right. Um, yes. So I think Tanushi, the organizers did say that it'll be available. Yeah. All right. Okay. Okay. So that is to give you an understanding of what is damped trend. Then you have multiplicative. Multiplicative would mean that you are looking at increasing variances. So your errors have to be multiplicative in nature. Okay. So these are the three taxonomies that you have on how your error is, how your trend is, and how your seasonality is. So exponential smoothing is always defined by these three character strings. Okay. Now, one does not manually look at each one of this. Your algorithm will give you the best fit model, which we will see in the next 5 minutes as we go further. Before I move to the R part of the screen there, I want to take you through the process of exponential smoothing fitting. So the first step, we will estimate the parameters. Then we look at something called as an information criterion. So in information criterion will basically help you understand the best fit model. Okay. Whichever model has the minimum information criterion, that will be the best fit among the various variants that you have within a particular class. Okay. So if I fit an exponential smoothing model A, let's say its AIC value is 5. I fit another exponential variant, its AIC value is 4. I'm going to pick the model with the minimum AIC as the best fit. AIC stands for Akaike Information Criterion. BIC stands for the Bayesian Information Criterion. I'm not getting into the deep dive math of it, but one needs to understand that information criterion is going to help you select the best model within a particular class among the different variants that you have within the exponential smoothing in this context. So once we fit the model, then we're going to look at generating forecasts followed by model validation. So we have some tests there. It's called the Young box test. We have the ACF plot of residuals. We'll also look at the histogram of residuals to look at how good the model is. And finally, we'll also look at the forecast accuracy measures. There are different measures. You have the mean absolute error, the MAE. RMSE stands for the root mean square error. MAPE stands for the mean absolute percentage error. Okay, so this is going to be typically the flow of checking or fitting a particular model and looking at model validation. So having said this, I'm just going back to the R screen. Okay. Those are working parallelly with me, please run the code. Otherwise, watch this as I take you through the steps. Right. So I have converted to a time series object here. And now we're building the model. Okay, so let me take you through the model arguments here. I'm calling it as model 1. ETS is the exponential smoothing. You're doing it on your time series object. So you see the triple Z here, which actually indicates the three strings I explained to you. The first one will stand for the error, the nature of the error, whether it's an additive or a multiplicative error that you're fitting. Second will be the trend, and the third will be the string for the seasonality. Now, whenever I define all by a null, it means that that's the default in which you will define your code. Alpha, beta, gamma, phi are all going to be a different parameters. Alpha will be the smoothing parameter. Beta is going to be a second parameter connected to the trend. Gamma will come in only if there is seasonality. And phi is going to be a parameter if I'm going to see not a steady trend, but a dampening of trend. So I'm going to set it null as a default. The model is going to run and I will get outputs finally based on which I will decide and understand what is there. Okay. So we also give the lower and the upper bounds. So all these parameters, whether it's alpha, beta, gamma, or phi, they range between 0 and 1. Okay, so that's going to be the range of the parameter. And I told you the optimization criterion, that's the opt.criteria. Here we're looking at minimizing the errors, so mean square errors. So that is fixed there. And we're allowing multiplicative trend in the model, right? So if you say fit an ETS model, all these are the arguments which are going to come with it. And we just need to run it. I've also given you a description of all these arguments, what I just explained now. All you need to say is give me a summary of the model. Okay, so this is something that we should understand. So I'm coming to the summary of the model. So please look at what we have. We actually got an ETS AAN. So this is a model which has come to me as the best fit. So what do I mean by an AAN? So when I say AAN, the first string stands for additive errors, which means there is no heavy variability in the time series data here. So it's fixed the additive errors. And it's fixed additive trend, which means trend definitely exists, but very clearly even the graph tells me that it's not a continuous or a steep increase or a steep decrease. So it is an additive trend model. And there is no significant seasonality. So as per the model fit here, there is no significant seasonality, and that is why the N is built here. So I have to look at the model here typically being an additive trend model. All right. Now let's look at what the parameters are. So I told you there are two parameters here. Alpha is called a smoothing parameter. So that's the model fixed, the value of the parameter. Then you have beta, which is called as a growth parameter. So let me pause here and explain. I will also give you the model equation just for you to appreciate what exactly it is at a later stage. So I have two parameters here. Both alpha and beta range between 0 and 1. So the closer alpha is to 0, it means that very minimal weightage is given to the most recent observations, which means if I'm going to look at, say, predicting, let's say I have totally historical data points, 100 data points, okay? If I'm predicting the 101st, all right, and if I'm looking at a very small alpha value here, it means very recent observations, like immediate past data, say the 100 or the 99, 98, immediate observations are going to have very minimal weightage. So the way the forecast is going to come in this context basically means that the model relies more on the previous period. So the historical trend becomes much more important. The past data values become more important in predicting the future. That is how I understand a low alpha value. Let's say alpha was very close to 1. Okay. So let's say it is 0.9, 0.8. Then it would mean that, say, yesterday's value or, the time lag or 2 days before. I'm just giving you an example. I'm trying to say that recent observations are having more impact on the future than the historical data. That's the understanding of what you can get from your alpha and from alpha. Okay, so I hope that interpretation of alpha is clear, right? Next one, I'm looking at beta. It's not like a steady increase or a steady decrease that I see here. So this beta basically stands for the growth parameter. Now, once I have the parameter, I also have the initial states. My first value of L and beta, L is connected to my baseline value. So 11.71 is my baseline value, and my initial trend value is what I get, which is say 0.3892. So let me tell you how this model will look like. I'll probably share my whiteboard at this time. Just give me a minute. Weather is unpredictable today. How can it? So it depends on the data, right? I'm not talking about weather in this context. So this is the output that I'm getting from the sales data that I have. So it tells you, see, time series has historical dependence, Sthiti, okay? It has historical dependence, but how much weightage, which part of the data of the past has on the future depends upon that particular data set, right? And that is where I'm having a model which is going to tell me that, okay? Time series has historical dependence. But whether the immediate last 10 observations have the greatest impact on the future, or whether it is really the past data, maybe even the previous 20, 30 data points are impacting the future, depends upon the data that we have. So I want you to understand that perspective. Let me just give you the equation here. I'm just opening a whiteboard here. That'll actually help me write the equation. Yeah. So let me just give you the equation just for you to appreciate how my model is going to be in this case. Okay, these are statistical models. So my model basically is this: LT will be equal to alpha YT plus 1 minus alpha. My pen is just a little weird, so I'm just writing it. Please excuse me for that. LT minus 1 plus BT minus 1. Okay. Only for one, I'm going to show you so that you understand how the model actually comes through. Then I will have BT. I will explain this to you, which is beta into LT minus LT minus 1 plus 1 minus beta. This is your exponential smoothing model. BT minus 1. So T minus 1 is basically the past value. So overall, my forecast will be Y hat T plus H, where H is actually your forecasting horizon, or it's called the forecasting period. Say I want to forecast for the next day in this context, sales volume for the next day. Okay. This is going to be a sum of your LT plus H into BT. So in this, what I want you to understand is this. So when I talk about LT, the initial value of L is what we got from the, this modeling, 11.78. YT will represent your observations, right? And we got alpha, which is nothing but a smoothing parameter. So if I know alpha, I know 1 minus alpha, right? LT minus 1 is basically going to be the previous value. So I will find L1, I will find L2, I will find L3. So to find L1, I need the L naught, right? At t equal to 1. That L naught is what you got as 11.78. So that's like your baseline value. Then you also have another parameter, estimate, which is your initial value, which is your B naught, which is 0.3892. When I go back to the R screen, I will show you that again. So based on that value, I will find B1, B2, B3, B4, so on. And this depends upon beta. So basically you have the beta, the second equation, what I've put there, which is going to give you the trend evolution. So both of these put together, the smoothening as well as analysis of the trend part, will help you get the forecasts. So the combination of L and B is going to give you the subsequent forecast. When I say Y hat, I'm basically talking about the estimate or the prediction. So what are the various things we need in this model for predictions? We need our initial values, that's your L naught and B naught, which we got. And you also need your smoothing parameter and growth parameter, which is alpha and beta. So these are your parameters to actually build your fits as well as forecasts. Got a sense of the model. One need not remember, every part of the model, but only when you see the model, you will kind of appreciate what those various elements in the output that we've got are. So I hope this broadly you're able to understand this. Yeah, Shruti, yes, I will share the PPT, everything I will share. I'll share the, what I have here, everything will be shared. Yeah. So I hope this is clear and you're with me. If not completely, you got a sense of, what we're doing here. Yeah. Okay. So now I'm going to go back and share my screen. I'm going straight to the R screen. Yes. So that's how these four values come. And now I'm going to the AIC. So it has already given me, when I run this ETS, right, the exponential smoothing model, it's going to run through the entire variants. It's going to try all the different ETS variants. There are about 15 variants that I showed you. It's going to run the different exponential smoothing model and give me the best fit model. My best fit model is the AAN, which I've fixed here. For that, it's going to give me the information criterion. That's the AIC value here. There are a couple of outputs that we'll get. I'm only interpreting the most important ones. And going further, I want to take you through, there are different error metrics. I will just take you through the RMSE here, right? The RMSE is 5.04 here. So typically, how do you use this RMSE? So I'm building my model using the trained data set. And later, when I apply the same model on the test, my error matrices should be comparable, which means the RMSE, what I get for the train, should be comparable with what I get for the test for me to say that my model is working good, in addition to the various assumptions that we will validate. Okay, so in this slide, the RMSE is important. I just want you to remember that we saw an RMSE of 5.04 here. Let me now run it on the test data. So I'll take you through that and then pause for any doubts that you might have on the exponential smoothing. Okay, so I'll quickly run these steps. So I'm generating the fits. Please take a look at it. When I say fits, when I run the fit, it's going to generate the fits for my trained data. I can also plot the fits. So this is going to be the plot what I get of the fits. Now, whenever you forecast, please remember the exponential smoothing is going to give you point forecast. When I say point forecast, it's going to give you a single value, single forecasted value, which means the next day's sales volume. But I also wanted to forecast with a confidence interval, right? When I say confidence interval, it's going to tell me the range around which my forecast is likely to lie. Okay. So I run my forecast function on the model. H is basically the forecasting period. So let's say I want to forecast for the next 80 days. And level is equal to C95. Here I'm forecasting with a 95% confidence interval. Okay. So I'm running my forecast function. So you see that my forecasts are generated. So if I look at my output here, after 170 observations, it's going to generate it all for my remaining observations. So look at the point forecasts which are generated along with confidence interval. So for example, if I look at 40, right? This tells me that the sales on the 171st day should be 40 units. It could be in thousands or lakhs as the data demands for. And it is going to range between 30 and 50. This is larger, right? Yeah, I'll answer your question, Shruti, after I finish this segment. And I'm setting a forecast function here. I'll tell you why we're doing this as we go further. So I'm just setting a forecast function where the input value is defined and I'm having a forecast horizon. The reason for defining it will be explained as we go a little further. Then we have we'll go to evaluate residuals, which is very important. I want to look at model validation at the next step. So I'm just redefining my y as trained, and my expected values are the fitted values that I get. So basically I've got my y hat, and y minus y hat is a residual which I'm getting from my train. So these are all the residuals, and it's important to look at the residuals. So under residuals, there are two important things to look at. When I do the check residuals, I run what is called as the Young box test. So the Young box test is basically going to tell us how good the model is, right? So this is a hypothesis test where my null hypothesis will tell me that there are no significant autocorrelation in the residuals, and my alternative will emphasize that the residuals have serial correlation. Now, why is this important? When I'm doing time series analysis, it's important to understand how my residuals behave. So if my residuals are having correlation, if they exhibit serial correlation or inherent interaction between each other, it means that the model is not really capturing things in a good way. Okay, so what I'm trying to say is, if my model is capturing most of my information, then I should not see any patterns in residuals. This is what is validated by the Young box test. So every hypothesis test is defined by a null and its alternative, which is what I told you for the Young box test as well. So my p-value here comes out to be 0.5, which is more than 0.05. It is tested at 5% level of significance, which tells me that there is no serial correlation in the residuals. Okay, so this is desirable. We do not want serial correlation. If my p-value was less than 0.05, it would imply that my residuals have serial correlation. So this is one important thing I should check. I could also check this visually. Okay, so I have something called as the ACF for the autocorrelation function plot. So I want you to look at the ACF plot that we have. Okay, so I'm just going to look at the ACF plot here. You see that for across all the lag values here, ACF stands for autocorrelation function. They are well within these two blue lines. Okay, so this is a visual validation of the test which I just told you, where I see that the residuals are not autocorrelated. And I would also want to look at the histogram of the residuals. I'm just plotting the histogram of the residuals, which is not exactly symmetric. This kind of points to normality of residuals. You see a bell coming there. Okay, so fairly indicating that my residuals are having a normal distribution. Now what I'm going to do is I'm going to run this model on my test data. So please remember, we've built these parameters, whether it be L or beta, we've built this on the trained data. I'm going to apply this on the test, which is from 171 to 243 observations. I'm applying this there and I'm building a summary. So in this summary, I only want you to observe that my RMSE value on the test is around 10 point something. So we saw it was around 5 point for the train and it's around 10 for the test. So usually my error matrices should be comparable for me to say that my data is actually, my model is actually working well. So somewhere I just want to show you the forecast here. Let me zoom and show you the forecast. So please observe this. This is the forecast that we have with the confidence level. So you see that as we are moving towards, forecast beyond 243 observations, you see that the gray area is really bigger, right? So my predictions are not that accurate, which is what is also reflected by the RMSE. My RMSE for train and the root mean square error for test should be comparable. Okay, so exponential smoothing is one of the models, but I don't think it's really a best fit here. We could look at other models, and that is where I want to answer your question, Shruti. When we start modeling, right? So usually you want to build a baseline model, and exponential smoothing is among the first that you would try. And then you can look at ARIMA models, which I would be discussing. And ARIMA typically captures linearity, and it's going to capture dependency in the data observations in a very good way. But however, ARIMA has its own limitations. It's good for linear models. The third model, which I might very quickly skim through, is going to be the NNAR, which is a neural network autoregressive. So this is an autoregressive or an ARIMA variant which will capture nonlinearity very well. And as I run through my discussion, I want to show you that when we run various models, we'll see that the NNAR will be a very good fit to this particular data. So whenever you look at modeling, one needs to understand that you try and actually go through the iterative process, running through different classes of models, and then you finally arrive at the best fit, right? Particularly if I want to capture long-term dependencies, you can also look at a long short-term memory model. LSTM is very good to capture long-term dependencies. That's a deep learning model which is used. So I hope I have broadly answered your question. Yeah, okay. So I just want to pause here and just want to understand if you have any doubts on the exponential smoothing. Otherwise, I will move on to the next one. That's ARIMA and also take you through the NNAR. I just want to know how much time I have, Shruti, so that I can, accordingly discuss.
Uh, I think you can take 20 minutes more.
Okay, sure.
Yeah,
I'll do that.
yeah.
Perfect.
Okay.
All right. So I would not run it line by line. I'm going to go a little quickly on to the next part. So when I'm running ARIMA, so let me tell you, ARIMA stands for, okay, so ARIMA stands for Autoregressive Integrated Moving Average. So when you're running ARIMA model, the first thing that you look at is the test for stationarity, which means you want your time series data to be stable across having constant mean variance, and it should not really change over time. So it is important to ensure that your data is stationary before you do your modeling. Okay, particularly ARIMA requires that. The I takes care of how many times I have to difference the series so that I can bring it down to a stationary series. So I need you to understand that stationarity is like one of the fundamental assumptions that you have to check for before you proceed. Now in ARIMA, you have again three parameters, P, D, and Q. P stands for the autoregressive terms, uh, which is nothing but the number of lag observations included in the model. What do I mean by lag observations? So I'm talking about how many observations of the past are important to predict the future. For example, if I tell you P is equal to 5, it means that every successive value will have dependency on the 5 previous preceding values. That's P for me. That's the first parameter. D will stand for, PDQ is the parameter order. D will stand for the number of times I have to difference to make the series stationary. Okay, so we'll run through the ADF test as well. And Q will stand for the order of the moving average. So when you're talking about moving average here, Q will tell you the number of past forecast errors which are used in the model. So if I tell you Q is equal to 5, it means that 5 values with respect to the errors would be having an impact on my future forecasts. Okay, so ARIMA basically is a 3-parameter model, and I'll quickly run you through the ARIMA here. So typically, you'll have to do through the train test, etc. But I'm not splitting the data, right? I'm just running it through my full data because I want to show you that ARIMA would probably perform slightly better than the exponential smoothing. But we'll see that the last model, the NNAR, when I apply a non-linear variant, combining the neural network concept, that will turn out much better compared to the exponential smoothing as well as the ARIMA. Okay, so that's a discussion I want to converge to. So I'm going to define y1, which is my data point. Please look at the length of y1. That's like my entire 243 data points. I'm just building my ARIMA model on this. So I'll run through all the tests and things that I told you now. First, I'm converting it to a time series object. I will load this package of T series and I'm running my ADF test. ADF stands for the augmented decay Fuller test. Now, my p value here is more than 0.05. confirming that my series is non-stationary, okay? Please remember, stationarity is a requirement. So I have to convert it to a stationary data. I'm not manually running it. So in R, you have something called as an auto arima function. So again, within arima, what should be the different arima model, which, what can be the various combination of parameters is what I run through the auto arima here. So let me just take you through this. When I run this, and I'm going to open the output for you, excuse me, this is what I see. So you see that various combinations of PDQ are defined here, right? And for each, I'm going to get the corresponding AIC value. And it's telling me that the best model is ARIMA 112. So ARIMA 112 means P is equal to 1. That's the number of autoregressive or lag terms required. Differencing 1, which means I have to difference the series 1. What do I mean by differencing here? It's basically doing y2 minus y1, y3 minus y2. So successive data observations are differenced. And Q is equal to 2 here, which means I need two moving average terms. That's basically the order of the moving average or the number of past forecast errors which are used in the model, right? So it gives me the best. How do I get this best model? That's one pointer to note. The best model will correspond to the minimum Akaike information criterion. If you remember, I started the discussion with the information criterion. So in this, you see that 112 ARIMA model will correspond to the minimum AIC value in this entire range. So that's how I get my ARIMA model. So it goes through the iterative process to decide the best fit. So once I get that, yeah, I'll go to the main parts of it, all right? Now I'm going to fit the model. I run, now that I know 112 is the best fit, I'm on line 124. Model 2 is going to be my ARIMA model, which I'm fitting 112 on the time series data. And I get the summary of the model. So again, I have my RMSE value at around 5.21. So that's my root mean square error. I can also look at, before I come to this cross validation, I'll just talk about the concept, but I'll show you the fitted values coming from ARIMA, and I will plot the forecast. So you can plot at a 90 or a 95%. So this is my corresponding ARIMA forecast that I have. Yes. Just give me a minute. So this is the forecast that you see. You can see what I've zoomed and I've shown you. So definitely it might work out to be a little more better compared to the exponential smoothing. You see the shorter confidence intervals here, right? But when I look at, yes, Shruti, it looks better, right? But if I see, when I actually, apply the train test and look at it, it might not be extremely good compared to the ETS or the exponential smoothing. It's slightly better than the model. But for model validation, I must also couple it with a residual analysis. So I'm showing you a residual analysis in one frame, all right? So my residuals are fairly random, and my ACF plot for the residuals is well within the significant bounds. Largely normal residuals. I can look at the residuals to be fairly normal, fairly symmetric looking at the graph here. So this residual diagnosis is important for me to be convinced that the ARIMA model works well. But in compared to the ETS, I have to actually look at the RMSE values, which is not heavily, different. I see my RMSE values around, say, 5.29 here as well. So what I want to do next is take you through a pointer called cross-validation, okay? So see, when I'm fitting, let us understand these two pointers. When I look at information criterion or the AIC value which you saw is going to tell you within, when I'm fitting different types of ARIMA models, which is the best fit, ARIMA model. But if I have to compare across different models, right, I do it using a technique of what is called as time series cross validation. So this is something that you should really look up and understand on literature. I'm going to take you briefly through this part. So what I do in time series cross validation is, this is one of the best methods to find out which of the models perform better when you're comparing across different models. Okay. So I will find out the cross validation. I'll run time series cross validation and compute my error here. I'll also do it for both ETS and ARIMA. So I'm running my cross validation, and I want you to understand that it's the, RMSE that I'm actually computing here on running this cross validation. So this is the value I need to actually look at. 4.39 is the cross validation error value which I got with respect to ETS. And when I run the same thing on ARIMA, yeah, I might have to run the previous part here. I get a NaN value because I've quite not run the previous part. Just give me a moment. Yes. So I have my cross validation error of around 4.43 for ARIMA. So please see that it's, it might not on this particular time series data, right? My exponential smoothing works out to be 4.39 ARIMA. I've run it on the entire data, while exponential smoothing, I actually did it for the train. So they are fairly comparable. So it's not like ARIMA's outperforming exponential smoothing as well. So if a model performs better than the other, its cross-validation error should come down significantly, okay? So that's how I compare across models. Now I'm going to the NNAR. Yeah, so ARIMA slightly is a little better. So you will see that I have run, my exponential smoothing only on the train, while ARIMA, for quick understanding, I ran it on the entire data set. But you'll see that ARIMA will have a very smaller difference in the cross-validation error compared to ETS. So it might not be very good after all. Fairly similar, okay? Not really very significantly different in giving the forecasts. You're right. I want to run the NNAR model, and I'll also tell you what this NNAR basically does and what are its parameters. Okay, so I will spend maybe another 5 minutes and I'll wrap this. So when I'm running the NNAR model here, you have the neater package here, the N-neater package, which is basically going to help you run this model. Now, NNAR has, let me point this out. I'm running my model and then I'll explain the summary, okay? So I'm running my model here. And the model which I get here is NNAR 53. NNAR stands for Neural Network Autoregressive. So this value, I'm just putting it here with a hashtag. The value of 5 is basically standing for P. And this stands for the number of autoregressive terms in the model. Same meaning as what we saw in ARIMA. But the value of K is different. K is equal to 3 here, where this stands for the number of nodes in one hidden layer. So basically, when you look at a neural network concept, I want you to understand that your input is going to be your time series value, right? Your time series observations. And what happens in a neural network, I'm only explaining it in a very broad way. In a neural network, you have multiple layers that your data is going to go through. So you basically call them as hidden layers, right? And output of one hidden layer is going to become the input to the next hidden layer. So basically, it's an iterative process which will run, which is not going to be kind of seen by you. And this mathematically happens through what is called as an activation function, right? That's how the internal modeling will happen. And finally, you will get your output. So neural networks are basically, they work like the neurons in your brain. That's how the whole deep learning concept evolved. So when I'm running neural network here, uh, the kind of output I get is fairly different. Largely, your neural networks can perform much better than simpler models because of the very fundamental fact that they will capture non-linearity. That's a basic difference. When I look at ARIMA or the other models that we discussed, or even exponential smoothing for that matter, really does not capture non-linearity very effectively. In ARIMA, I'm differencing the series, but still, it doesn't help me capture non-linearity the way a neural network model will do, right? So given that part, I will see that when I run the cross-validation here, the cross-validation error will be fairly lesser. So before that, I just want to simulate and show you uh, how exactly the forecast will come here. Give me a moment. Right. So I want to just show you the forecast here. So I'm running through different NNER models here. And finally, I will show you one forecast model. It's still running here. Probably my internet is a little slow. I've still not got the next plot. And I'm going to show you a joint plot. So when you run this, you will see a plot of ARIMA, NNAR. You can also combine and show them. It's just having a little bit of bandwidth problem, I guess. It's coming up. Just give me a moment. So I've shown you plots of ARIMA, NNAR together, right? And I want you to interestingly watch the cross-validation error. My cross-validation error, yeah, we can try it out, sure, yes. So my cross-validation error will work out to be around 3 point something. I'd just like to show that to you, and yes, 3.9. So you see that significantly my error drops when I apply the NNAR. The last few steps are again validating the residuals in terms of seeing whether the residuals are normal and whether they are autocorrelated. So yeah, that's typically how you're going to work on the modeling part. So going very quickly to the non-linear neural network. So I want to emphasize that we've tried the exponential smoothing, the ARIMA, as well as the NNAR model. And we see that for this particular data set, the NNAR performs much better, and the cross-validation error is the way in which you will highlight and figure out which is much better. When you're usually using an approach of ML, you divide your data into train and test, and you can also cross-compare between RMSE of train and test. They should also be comparable. So multiple things we have to look at in terms of model validation. So I hope I have been able to give you, yes, sure. So I'm going to stop. I'm done with the session. So yes. So I just want to leave you with this. And I'm open for quick questions or interaction. You can connect with me on LinkedIn. You can write out to me. Time series is an area that I work on. So if you think you have more questions, you want to discuss something in particular, please write out to me. That's my email ID. I'm available for interactions. You can also connect with me on LinkedIn. I'm pretty active there. Thank you so much.
Thank you so much, ma'am. It was really very interesting session, and my mind is like quite blown away. I know there are a lot of like information for a lot of
Absolutely.
students, but I hope participants has enjoyed it, and please do send
I hope.
us yeah, do send us
Sure.
our feedback, uh, and I will share the feedback form link in a while. And first, before winding up, thank you so much again, ma'am, for giving your time and patience to go through all these very interesting methods. And the recording will be available. And please, once you share the PDF of your of the files, I will upload it
Sure.
along with the recording, so that participants can practice this in their own time as well. So thank you
Absolutely.
again,
I'll
ma'am.
mail it to you.
Thank
Yeah,
you,
thank you.
ma'am. It was a pleasure having you here, and maybe hope to see you in other workshops in future as well.
Sure. Sure.
Yeah.
Thank you,
So,
Shruti.
yeah,
If
thank you, ma'am.
if it's all right, I would like the participants, if it's okay, they could just turn their videos on for a split second, probably tell hello and take a
Yes,
screenshot.
please. Yes, yes.
Yeah.
Please, participants, please could you switch on your
Not mandatory, but yeah, since we're online, it's always nice to see.
to
Yeah.
see, yeah,
Great. Thank you. Thank you, Mr. Sanjay. Yeah. All right. So
other.
thank you, everyone. I hope you enjoyed the session, and we'll have continued interaction. Thank you so much, Shruti and May, for inviting me. Had a great time. Thank you.
Thank you, thank you.
Pleasure.
And let me share the feedback form and then we can conclude. Give me 1 second. Any questions in between? Anyone wants
Yeah,
to like
absolutely.
any questions, anything, any, because she's so much experience now. Even if it is not particularly to time series, maybe you can ask about career or life or whatever.
Yeah, I'm good. I'm basically a teacher, so
Yes.
uh, I'm sure this and it's something that I can share always. Yeah, right.
No questions?
All right.
So maybe they can go through the material and later on can. So this is the feedback form. Please do fill it up. Share us your inputs and so that we can keep doing these kind of workshops. All right. Okay. So thank you all. Thank you, ma'am.
Thank
Thank you
you.
so much.
Thank you very much.
Yeah.
Thank you.
Bye bye. Bye bye.